Good afternoon, everyone, and welcome to the January 2025 edition of Innovation Insights. As we embark upon a new year and IACMI's 10th anniversary year, we look forward to being able to continue to provide you with great content every month of the year during Innovation Insights. Just a couple of things I want to go through. Just reminding the broad value offering to members of the Convene and Connect catalyzed through lots of various forms, including in-person and events like today. And if you're not an IACMI member and you'd like to become one, go to iacmi.org/members and sign up there, and we will get in touch with you to help you get going on that process. And we do have about 170 members of IACMI, company members of IACMI, and we'd love to have those of you that aren't members to become members. Just a couple of points in here on save the date. Our annual members meeting will be June 24th through 26th in Dayton, Ohio. And we look forward to celebrating our 10th anniversary at that time. And then a little bit prior to that, new facility, IACMI-based facility in Knoxville, Tennessee, housing the fibers and composites manufacturing facility and IACMI's headquarters has just been erected. And we will be having an open house at that February 19th at 2 p.m. Everyone is invited to attend that. Kim, if you've got the link for that and want to put that in the chat, you can do that. And we'll move on to today's business. Just a reminder that all of our webinars are on our website. You can go back and actually watch the video of every one of them, 31 episodes since May 2021. We've featured over 100 IACMI members and research partners on that. And we've already got the schedule outlined for the year, but we'll just put these out until May. They'll be on Mondays, February, March, April, and May. And we do still have some presenter slots available for March, April, and May. June, we will not have Innovation Insights because it is our members meeting month. And so we'll have that instead then. We've got a great lineup today, great presentations. First from Vanderbilt University and Rowan University, and then from Joe Fox, who's a consultant to IACMI and been working on a project for IACMI called Innovation, called IACMI Impact. And we will give Joe a little bit of the extra time to go through that. So at the moment, I'm going to go ahead and hand the floor over to our friends from Vanderbilt and Rowan, to Sankaran Mahadevan and Paramita Nath. So Paramita, if you want to go ahead and share, I'll let you do that. Let me try to get to my stop sharing.
Thank you, Dale, for introducing us, and thanks to IACMI for the opportunity to present our work. Particularly thanks to my colleague Doug Adams for connecting us with Kim and making this happen.
Okay, Paramita, can you put it into slideshow mode? Yeah.
Thank you. So I'm going to just make a few remarks opening, and then turn it over to Paramita, and then I'm going to come back and close it out with the last slide. The work that Paramita will be presenting here is based on her PhD work here at Vanderbilt. And this is all funded by NIST. We've had NIST funding for the last 10 years on various aspects of manufacturing and additive manufacturing especially, and particularly addressing the uncertainties and variabilities in the manufacturing process and the computational models that are used to describe the manufacturing process. And so we've used all those ideas in putting together a digital twin concept for design and control of manufacturing processes. We have, of course, show this for metals additive manufacturing, but we'll also see how that goes on to composites and other things. And this NIST project is what is being presented here, but now we are also part of a large team of a NASA STRI project on developing digital twin for supporting qualification and certification of additively manufactured parts, and also NREL project on additively manufactured wind turbine blade core. This has already led to a couple of other newer initiatives that I will talk about at the end. So now I'll hand it over to Paramita to describe the technical aspects of her work.
Thank you, Dr. Maha, and good afternoon, everyone. So as Dr. Maha said, we will be talking about digital twins, and most of my work on digital twin has been with respect to additive manufacturing, or commonly known as 3D printing. However, the concepts that we discuss does apply to almost all manufacturing techniques, and even outside of manufacturing world, and we could think of the digital twin in any field that we would like to. So what is the idea when we are manufacturing something? The main idea is that we want to have a good product of great quality. Now, the product quality depends on a few things, and the major ones are the process parameters. So what is process parameter? Process parameter is basically the parameters that are used in the manufacturing processes. If we think of a CNC machine, for example, then the process parameter could be the depth of the cut. If we are thinking of additive manufacturing, the three main process parameters are the power or the temperature of the heat source, the velocity of the heat source, the layer thickness, and so on. The product quality also depends on other variables like the ambient conditions. One time we were working on our research lab and things just don't work out, and we figured out it was because of the vent that was directly blowing air into the printer. So those things also are important when we are thinking about product quality. Raw material is another major concern when you are working with any kind of manufacturing techniques, and obviously the equipment and the skill of the human resources working on the manufacturing processes. Now, if there are quality issues, it could lead to different kinds of problems for the manufacturer, major ones being the customer dissatisfaction. There would be inefficiencies in the production process. We also run the risk of not meeting the regulatory compliance issues, and then obviously the major concern being increased costs. So the idea is, if there is a manufacturing process, we want it to be optimized so that we have products of consistent quality. Now, how do we do that? If we want to have product of consistent quality, how do we do that? We have to optimize the manufacturing process. Now, over the years, this optimization technique has changed. So initially, people would do a design of experiments and then conduct physical experiments, which was basically a trial and error process. Let me try these manufacturing parameters. Does it help? And does it improve my product quality? As you would imagine, if you're doing this repeated manufacturing physically, you're going to waste a lot of raw materials and energy. So then there was a shift towards model-based engineering. So in model-based engineering, people now create a physics-based model approach. And with that, instead of doing the trial and error in a lab or in a manufacturing process physically, you are doing that with the physics-based models. Now, no model is perfect. There are a lot of assumptions, and then there are simplifications when we are trying to solve those partial differential equations. So these may be inaccurate, and there tends to be a lot of inaccuracy related to that. So then there was a lot of work on this integrated approach of using physical models in conjunction with a few experimental data. So the idea being the physics model's prediction can now be corrected by using some experimental data. And now we can use this physics model, the corrected physics model, to optimize the manufacturing process, which leads to a more efficient overall approach. Now, what happens when we have a manufacturing process? There is a lot of variability which is inherent to the system. So let's say you get some powder for your of the raw material for an additive manufacturing process. The powder quality is not going to be consistent. It varies across different manufacturers. It might also be different for the same manufacturer. We need to be able to take that into account. Otherwise, we will end up with products which have variable quality. Now, we talked about model-based approach. The moment we add a model into the mix of our optimization process, we are adding more sources of uncertainty. And these sources of uncertainty are different from the ones that we have because of inherent variability. This is coming from our lack of knowledge about the model in general, and these are called epistemic uncertainty. That could come from the differences in the model parameters. We may not know the exact value. We may not have the exactly correct model itself. There may be uncertainty in the input to the models and so on. Some people think, well, models have so many issues, I'll just do with experiments, but that also does not work very well. There are errors in the experiment due to the human error. There could be equipment error and so on. So basically, we cannot get rid of these uncertainties. What we do have to do, though, is can we identify these uncertainties, reduce them, and so on. So if we look at a model as such, it has some input, it has some parameters. Now, if there is uncertainty in the input and the parameters, your output is going to be uncertain. Now, if the output is going to be uncertain, we need to now account for this variability and uncertainty. So there are two things that we do. One is the forward propagation, where we first identify where is this uncertainty even coming from, which parameters are leading to more uncertainty. So we do sensitivity analysis and stuff like that. And then we focus on reducing the uncertainty. Can I collect some more data and reduce the uncertainty in my model prediction? Can I characterize this using better experiments? Can I calibrate and validate my models? Now, you can do so far with the quantification and reduction of uncertainty, and then we are left with some uncertainty that needs to be managed, and that is where the process optimization and process control under uncertainty comes into the picture. Now, when we do process optimization, I would like you to understand the differences between the process optimization and process control. In process optimization, we use the information about the manufacturing process before the process has started. So we take the information that we have earlier and we do the process optimization. We have, we want to, our objective function for this optimization formulation is gonna be, we want to have the best quality, we want to minimize cost, we want to minimize time, and so on. But this information is based on things that have been happening before our manufacturing started. Now, during manufacturing, things tend to go wrong. There might be something that happens during manufacturing that was not considered earlier, and that leads to the need for the most up-to-date knowledge during manufacturing, and that is process control. So now, if we want to do process control, the approach that we use is model-based predictive control approach, and that leads to the concept of digital twin. Now, as we have talked about earlier, these digital twin depends on some models. There are so many uncertainties in there. So when we want to consider these uncertainty, we end up with a probabilistic digital twin. So our work is on probabilistic digital twin, which means there is a flavor of uncertainty quantification and management on the digital twin itself. Now, what is a digital twin? There have been many, many definitions of digital twin, and this paper by Vanderhoen and Mahadevan does look at all the different definitions. Now, the idea of digital twin was started by Michael Greaves, and that was way back. And his idea came from the life cycle product management. And the definition that is a robust definition for digital twin is that it is for a single instance of the physical system. And the data collected from this single instant is used to update the virtual representation. And over time, the digital twin represents this single instance with increasing fidelity. Now, this is an important thing to note because in the literature and even in the industry, digital twin is sometimes very often confused with simulation model. And there is a recent article by Greaves himself saying don't twin digital twins and simulations. So the simulation model is basically a representation of an imitation of the of the physical system itself. However, a digital twin has more elements to it that we would look at in the later slides. So the digital twin is a virtual representation of the physical system. However, this virtual representation is updated throughout the process by this exchange of information between the physical and the virtual representation. Now, if we look at the elements of the digital twin, there are three basic elements, and there are a lot of nomenclature related to that. This is the nomenclature that I'm going to use for the rest of our presentation. So a digital twin has the physical system that you're making a twin of. So this is the actual or the intended physical element, and this resides in the physical world. So this could be your CNC machine and the whole setup related to that. When you make a physics-based model or an analytical model of this physical system, that is the virtual representation of the digital world. And then we have several interconnections between them, the physical to the virtual connection, which is through the sensor data, data fusion, and model updating. And then we have the virtual to the physical connection, which communicates the decisions to the model. Right? So these are our three elements. Now, if you look at a laser powder bed fusion process, which is here this laser goes over the powder material layer upon layer till we get this final product. Now, if we have this product, how would we make a digital twin for this LPBF system? We'll start with this monitor, with this physical system, which consists of the machine itself. In 3D printing, we need a digital model, which is a CAD model that goes on. We have a monitoring system as well. For a digital twin, the monitoring system has to be online, non-destructive, and non-contact. So those are the requirements. Then we have a digital twins virtual representation, which is basically the physics-based models. Now, the physics-based models sometimes take days to run. So to make it more fast, we have to have a surrogate model. Most of the times, these are machine learning-based models. Then we also want to have a reliable model. That is where model validation with experiments come into the picture. Now, how do these interconnections work? For effective interconnections, the diagnosis and the inference are done using big data analysis and machine learning. And the model updating that we use, because we have a probabilistic digital twin, is the Bayesian inference. What it does is, depending on the data that we get from the physical system, we are now updating our virtual representation and making it more and more accurate to our physical process. Now, let's say we want to do a decision-making and a process control with respect to porosity in a 3D printed parts. Now, what is the idea here is that we use the digital twin to predict what is going to be the quality of the finished part. If the quality of the finished part is very similar to what our target was, we then continue the process as it is. If it is very, very poor, then we know that nothing we do is going to change much about this product, and the target quality is way too much higher, then we can then terminate the process, and then we can save on the material. And finally, if there is a slight difference which can actually be managed by changing the process parameters, by modifying your depth of the cut or by modifying the power and velocity and so on, then we use this decision-making system to change the process parameters. So this is an example from one of our works where we see that if we do not control the product quality by changing the process parameters, the porosity tends to keep increasing, leading to a part that is of not good compliance. Whereas if we keep changing the product, the manufacturing process, then our product quality is within the limit or within the target that we had. So this was all about the LPBF process, which is for additive manufacturing with metal. Now, we have been recently working towards the digital twin for composites in the additive manufacturing system as well, where we have a 3D printer with composites. Now, what we are doing is we are now looking at the process structure property relationship that we would then validate with experiments. Once you have this model set up for a composite where you know what should be the parameters depending on what is the quantity or what is the volume of your carbon fibers in the material, how do you then predict the macro scale properties using a simulation model here for a finite element model, for instance? And then how can we now tailor the microstructure so that we get composites that have the quality of product that we really need? Okay, so this would be, in short, an introduction to how digital twin works, and I'll bring it back to Dr. Maha for his concluding remarks.
Thank you, Paramita. So as I mentioned in the beginning, we are now taking these concepts that we developed with NIST funding and Paramita's PhD now to NASA STRI project that started last year. This is funded, it's a $15 million project over 5 years. It is 3 major university partners, Carnegie Mellon and Johns Hopkins and Vanderbilt, and also some other additional universities and industry partners, particularly Pratt & Whitney. And as you can see here, there are many different, now we are building this digital twin to support qualification and certification of additively manufactured metal components. That is actually, as Paramita mentioned in the beginning, there is, because of all the variability, there is tremendous challenge in qualifying and certification additively manufactured products. So there are, as for various steps, as you can see here, there are different teams involved, sub-teams involved, and all the green boxes you see have to do with quantifying and managing the uncertainty in the various aspects of the process. And then the left-hand side, you see all the yellow boxes are where the management and the optimizing and process control comes into play in order to meet the qualification and certification requirements. Of course, underlying all this is the building of the digital thread. The digital twin sits on top of the digital thread, which is also being built at Carnegie Mellon and Johns Hopkins. That's one very strong direction where we are going for the next 5 years. There is also the other project that, in fact, we are involved with Dale as well in that, is led by NREL on the additively manufactured core for the wind turbine blade. And Vanderbilt's involvement there through our laser resources is for quality monitoring of the additively manufactured core. Thank you for your attention, and we'll be happy to take any questions.
Okay, given our time frame right now, what I would suggest is that people put their questions in the chat or or in the Q&A panel, and you guys can get to those as they come along. The one question I just do want to ask is how do you see this progressing? What's the biggest leap that still needs to be made to implement this, say, in real time on machinery on the factory floor?
Excellent question. So far it has been in the research domain where we have demonstrated these ideas with very simple geometries and simple parts. What needs to be done is, first of all, to demonstrate these ideas with more complicated geometries and properties, number one. And then also, one of the important issues that always comes up is variability among machines. And that has not been addressed yet. And that is typically in a factory situation, that is a very important consideration.
Yeah, still work to go, but encouraging nonetheless.
Exactly.
Yeah. Thank you, Ma. Thank you, Paramita. Okay. Okay, our next speaker is Joe Fox. Joe is president of FX Consulting and has been working closely with us on a project around IACMI's first 10 years. Joe also serves on our IACMI Consortium Council as a chair appointee and has been very much a contributor to IACMI over the years, both in his full-time employment and previously with Ashland and Ineos, and then as an independent consultant. Joe, I'm going to turn it over to you.
Thank you very much, Dale. It's a pleasure to be here and have the opportunity to talk about a decade of innovation and IACMI's impact. So we are here, let's see if we are here to celebrate because in January of 2015, as this press release indicates, President Obama announced the creation of IACMI with a $70 million investment from the Department of Energy. And last Thursday, January 9th, 2025, IACMI celebrated the 10-year anniversary of that announcement. And it's hard to believe that it has been 10 years. I think most of the people in the audience are familiar with IACMI, but there may be a few newcomers. So here's some IACMI 101. IACMI stands for the Institute for Advanced Composites Manufacturing Innovation. It's also known as the Composites Institute. It is a Manufacturing USA Institute, one of 18 that have been created to revitalize U.S. manufacturing. It is a public-private partnership that brings together industry, academia, and the government. It was created in 2015 and then renewed in 2023. The press release in 2015 said that IACMI had 122 members when it is created. That number today is 172 members. So IACMI's membership has increased by 40% in the past decade. Its scope has also expanded, and I'll talk more about that as I proceed through my talk. This is probably one of the most important slides in my presentation. I've entitled it An Ecosystem of Innovation. I believe that's a very good description of what IACMI has become and what it continues to be. This figure was actually created by Chad Duty, IACMI's current CEO, and I think it does a very good description of what IACMI is all about. You have industrial members from all parts of the value chain, all sizes, all different industries. You have academic members. You have community colleges, universities, and trade schools. You have 2 federal laboratories, Oak Ridge and NREL, and you have federal and state agencies providing funding support. At the foundation of the ecosystem, you have IACMI's mission: convene, connect, and catalyze. You're going to hear those terms a lot as I proceed through the next 25 minutes. It's really how IACMI makes everything work. So this is what I call a voice of the customer slide. These are quotes from people who have been involved in that ecosystem. I'm not going to read it to you. I'm going to give you about 15 seconds to hear what other people have to say about IACMI. You're going to see more slides like this one. I want to come back to this slide, this figure, and I want you to focus on the 2 vertical elements: technical innovation and workforce development. They really are the 2 key pillars of IACMI, and you're going to hear a lot about them in the next 20 minutes as I proceed through my talk. On this slide, I want to focus on the roof, which Chad has termed better products, processes, and people. I think that's a very good qualitative description of what IACMI has delivered: better products, better processes, and better people. So as the 10-year anniversary was approaching, as Dale said, IACMI formed a team to quantify that impact as much as possible. The team consisted of Mark Morrison and Mark Slattery from IACMI's communications department and me. Our approach was to conduct interviews with stakeholders throughout the IACMI ecosystem. We said that we were collecting stories and stats. Margaret likes stories, I like stats, Mark likes them both, so we formed a very good team. We collected information in these 4 buckets: technical innovation, workforce development, collaborations, and leveraging IACMI's resources and reputation. And that's what you're going to hear about in the remainder of my talk. I'm going to weave in the mission: convene, connect, and catalyze, and you're also going to hear more voice of the customer. So let's begin with technical innovation. I call this slide Creating the Infrastructure of Innovation because IACMI has catalyzed the creation of $400 million of state-of-the-art facilities for R&D and for innovation in Colorado, Indiana, Michigan, Ohio, and Tennessee. This slide shows the resources or the facilities that have been built in Michigan, Colorado, and Indiana. These facilities enable research at scale, production-relevant research. And for example, the Scale Up Research Facility, or SURF facility in Detroit, contains one of the biggest compression molding presses and one of the biggest injection molding machines that I have ever seen. These facilities are shared spaces for innovation and for workforce development. The Comet facility at NREL has enabled the production of these large wind blade prototypes. And the Indiana Manufacturing Institute is the home to the Composites Manufacturing and Simulation Center, or CMSC, at Purdue. This slide shows some of the facilities that have been created in Tennessee and in Ohio. And this timeline is intended to show the creation of that infrastructure. Most of the activity occurred in the first 3 years. And creating this infrastructure for innovation has really catalyzed the technical innovation that I'm going to talk about next. So IACMI has catalyzed the completion of more than 60 R&D projects with a research portfolio valued at more than $150 million. Those projects have involved more than 90 IACMI members, and there are currently 5 R&D projects underway. These projects have been industry-led, and as Dale and former CEO John Hopkins would like to say, purpose-driven. Those are 2 very important attributes of IACMI projects. They have addressed key techno-economic challenges to the increased adoption of composites, and they have delivered supply chain-based solutions. You can find the project reports, the final reports for these projects, on the IACMI website. And these projects have resulted in dozens of publications and articles. So now I want to tell you about 4 technical innovation success stories for additive manufacturing, for the production of composite parts for vehicles, for the manufacturing of wind turbine blades, and for the recycling and reuse of composites. Success story number 1 has to do with additive manufacturing of composites and tooling. This is a great success story involving innovation and collaboration at Oak Ridge and Purdue that spans nearly the entire decade. It began with a project at Oak Ridge that used the Big Area Additive Manufacturing Equipment, or BAM, at the manufacturing demonstration facility at Oak Ridge. That equipment enables the production of very large 3D printed structures, like this car that Chad Duty is sitting in about 10 years ago. Professor Byron Pipes and his graduate student, Eduardo Brosius, saw what was happening at Oak Ridge, and they said, this is the future. So they began a project to model the additive manufacturing process, and they acquired their own large-scale additive manufacturing equipment to validate their models. Fast forward to 2022, when Dimensional Innovations worked with a team of IACMI members to create the world's largest 3D printed structure. And that is the Al Davis Memorial Torch at Allegiant Stadium in Las Vegas. The team consisted of Tecmer, a material supplier, Thermwood, an equipment supplier, and Purdue, which helped with the structural engineering analysis. This is a very good example of a supply chain-based solution, and IACMI catalyzed this collaboration. And you can see the fruits of that collaboration the next time you watch a Las Vegas Raiders football game on TV. Let's talk a little bit more about what is happening at Purdue. I said that they are the IACMI Center for Simulation and Modeling, and they are having a very big impact in the tooling industry because they are enabling and revolutionizing the 3D printing of tooling for advanced composites. They've done that by developing additive 3D software, which, like the Vandy folks have talked about, are the digital twin or the virtual twin of the additive manufacturing process. They have developed that in conjunction with Dassault Systems. And their approach is summarized here, where they have taken the large-scale additive manufacturing equipment plus the virtual twin to give tooling that is printed right the first time. That means that you have shorter production times for toolings, fewer tooling iterations, and that translates into lower overall tooling costs. This approach is being adopted by members of the Composites Additive Manufacturing and Simulation, or CAMS consortium at Purdue. And it is another very good example of where adoption of new technology, state-of-the-art technology developed by IACMI is having an impact. The second success story has to do with the production of composite parts for vehicles. This is an area where automotive OEMs like Ford and Volkswagen have leveraged IACMI's resources and expertise. They have used the equipment and the tooling and the fabrication expertise at the SURF facility in Detroit, and they have used the modeling and simulation expertise at Purdue. It's also another area where supply chain-based solutions have been created. For example, here you have Ford working with a host of material suppliers to demonstrate enabling technology with new resins, with carbon fibers, and with preprints. And over here, you have Volkswagen, again, working with an assortment of material suppliers to demonstrate the lighter weight, part consolidation, and inline painting benefits of composite parts like lift gates and hoods. The end result of these efforts are composite parts on vehicles from Ford, Volkswagen, and Hyundai that you will find on the road. Here's a picture of the Ford GT, the Santa Cruz from Hyundai, and some of the vehicles that are in the Volkswagen family that have what I call IACMI fingerprints on them. The third success story has to do with the manufacturing of wind turbine blades. And this is a very good example where IACMI efforts have led to steady and ongoing advancement of the technology readiness level, or TRL, of a technology. The technology here is the production of next generation wind turbine blades that have been demonstrated with Arkema's helium resin, which is a thermoplastic resin that processes like a thermoset. Now, commercial blades with helium have not been produced yet, but this timeline is going to show the steady increase in TRL that has occurred, because in 2016, this 9-meter blade was produced at the Comet facility at NREL. That's TRL 4. In 2018 and 2019, a 13-meter blade was fabricated, tested, and validated at NREL. That took the TRL up to 5. And in 2022, Arkema and LM Wind and members of the Zebra Consortium in Europe demonstrated this 62-meter blade, taking TRL, or blade fabrication with helium, up to TRL 7. IACMI has also improved the production of existing blades through the use of RFID tags, through inline quality monitoring, and through advancements in automated finishing. Success story number 4 has to do with the recycling and reuse of composites. And this is an area where IACMI has really taken a leadership role over the past decade, because they have catalyzed an enormous amount of activity in this area. There have been 13 projects, including these 2, involving more than 30 IACMI members, and a recycling and circular economy working group has been formed. IACMI efforts have demonstrated the recycling of both carbon fiber and glass fiber composites. For carbon fibers, I want to highlight Vartega and the Composites Recycling Technology Center. Recycled fibers from Vartega have been used to produce parts like this thermoplastic fender, and the CRTC has used recycled carbon fibers to produce these benches and other structures. On the glass front, Carbon Rivers has developed a process for producing recycled glass fibers that can be pelletized with thermoplastics to produce parts like this spray nozzle. I mentioned supply chain-based solutions, and here's another quote that I really like. IACMI has helped create supply chains for recycling composites. And it's important to note that those supply chains did not exist before IACMI. It's almost like they've created an ecosystem within an ecosystem. Let's talk a little bit about commercialization success stories. I mentioned the vehicles with IACMI fingerprints, but IACMI has also catalyzed the commercialization of more than 24 new and innovative products from upstream members. For example, I mentioned Vartega on the last slide. They have commercialized their Easy Feed Bundle product line, which consists of recycled carbon fibers and thermoplastics that can be used in processes like injection molding. Michelman has commercialized a family of sizings for use with carbon fibers known as hydrosized carbon. Sizings are the coatings that go onto fibers to make them more compatible with resins. And these hydrosized sizings are finding applications in numerous industries. A few more examples. When I was talking about the Al Davis torch, I mentioned Tecmer. They have commercialized a family of thermoplastics that have been customized for 3D printing, known as high-fill. Staying on the additive manufacturing front, Purdue has made their additive 3D software available for licensing in a whole host of additive manufacturing applications. And going back to vehicles, IDI has commercialized Class A SMC for automotive applications like the Hyundai Santa Cruz, but because of the improvements in surface quality that they demonstrated at SURF, they have also sold their Fortium SMC for non-automotive applications. So to kind of wrap up this section of the talk, in terms of technical innovation, IACMI has catalyzed the commercialization of more than 24 new and innovative products. They have steadily increased the technology readiness level in areas like wind blade production and 3D printing and recycling. They have improved the manufacturing of existing products. There are vehicles on the road with IACMI fingerprints on them, and they've catalyzed what I call headline-worthy stories like the Al Davis Memorial Torch. That's the technical innovation part of the story today. It's certainly not all of the technical innovation that IACMI has accomplished, but it's the story for now. Let's move on to the second bucket, workforce development. And I've coupled that here with job creation because they go hand in hand. Workforce development, that's the second key pillar when I was talking about the ecosystem. And this is an area where IACMI has excelled. It's also an area where there are a lot of stats because IACMI has created customized workforce development programs to revitalize manufacturing in composite fabrication, in machining, and in metal casting. And as this one-pager shows, there are a host of programs: the IACMI Internship Program, ACE, Metal, ACCP, Skills Crafters, and Integrate. No shortage of acronyms. These programs, these customized programs, have motivated students of all ages, from K to grade, to consider a job, a career in manufacturing. And they are preparing those students for both blue-collar and white-collar jobs, both now and in the future. And if you sum up all of the people that have been involved in these programs to date, the total number comes to greater than 18,000 people, and it is growing all the time. I want to highlight just a couple of those programs. I want to talk about the internship program, which was really a success story of IACMI 1.0, because IACMI has created more than 100 industrial internships for college students. These have been spread throughout its ecosystem. And it's important to highlight that these students have a 100% placement rate. 100% of them have been hired into industry, academia, or the federal labs, or been accepted into graduate school. Many of them were quickly hired by the companies that they interned with. And I'm pleased to announce that internships are a very important and very attractive element of IACMI 2.0, and students are being connected to opportunities in the coming year as I speak. These interns are not the only students who have been impacted by IACMI. Many other graduate and undergraduate students have received advanced training in fabrication of composites and in simulation and modeling. And here are some quotes about the internship program. Again, I'll let you read them, give you about 10 seconds. I really like the one from Will Hunkin, and I like this one down here that says exponential impact and ripple effect. Let's talk about ACE. ACE stands for America's Cutting Edge, and this is a DoD-sponsored program that is focused on training for CNC machining. That industry is very important to our nation's military. And this is definitely an area where IACMI has convened, because it has convened more than 12,400 online attendees for ACE training and more than 2,600 persons attendees for in-person training. Over 40 machine tool training centers are involved in this program, and as this bar chart shows, ACE continues to grow and grow. Let's talk about community college involvement in IACMI, because dozens of community colleges have become involved in IACMI's workforce development initiatives. This is an area where IACMI has definitely connected. It has connected community colleges to universities through innovative franchising and hub and spoke models, and it has connected students to local and regional employment opportunities. It's also an area that shows how IACMI has evolved and expanded. When IACMI was formed, it really involved just a handful of universities, a very strong handful of universities. But today, there are many, many, many more community colleges involved and universities involved in IACMI through its workforce development initiatives. It's almost another example of an ecosystem within an ecosystem. All right, let's talk about job creation, because it really does go hand in hand with workforce development. It's fair to say that IACMI has created hundreds of manufacturing, engineering, and design jobs in many different industries in many different parts of the value chain. I've already mentioned the highly successful internship program and the 100% placement rate. Here are pictures of 3 interns who have landed jobs, 2 in industry, 1 in academia. IACMI has also catalyzed the creation of new jobs at existing companies. Most people think of TPI as a wind blade manufacturer, but their exposure and their involvement with high-pressure resin transfer molding at the SURF facility in Detroit spurred them to increase the production of parts for automotive applications. And they have created more than 24 new engineering and manufacturing jobs in their automotive division, which is now known as Senvius. We'll talk about company attraction. And this is something that is very important to the state economic development agencies. IACMI's presence at Purdue has motivated both Yajima and Saab to establish new facilities in Indiana focused on composites for automotive applications. And I just love this quote from Glenn Richardson of Jobs Ohio, and that is that IACMI is an important part of the ecosystem of innovation that has attracted companies like Airbus and Joby to Ohio. IACMI has also catalyzed job creation at startups and at many small to medium enterprises, or SMEs, especially those focused on recycling, sustainability, and the circular economy. The startups here at the top of this slide, most of them have been spawned out of the University of Tennessee and/or at Oak Ridge, and most of them are located in Tennessee. But Orion Performance Materials is located in South Carolina, and Vartega is located in Colorado. These growing companies are creating dozens of new jobs. I want to finish up this section by talking about co-location and say that some of IACMI's industrial members have co-located facilities onto IACMI sites. You've already seen these pictures, you've already seen this timeline, but I want to add a few events to illustrate co-location, because in 2020, Volkswagen co-located its North American Innovation Hub on the campus of the University of Tennessee. That same year, Dassault Systems co-located its 3D Experience Center on the campus of Purdue. And in 2021, BASF co-located their North American additive manufacturing facilities at the SURF facility in Detroit. There are many benefits to this co-location. It's really a combination of job creation and workforce development. It also fosters collaboration between industry and academia, which is a very good thing. And I'm happy to report that there's going to be more opportunities for co-location and Innovation South as it opens on the University of Tennessee campus. And again, Dale mentioned the open house on February the 19th. So we've talked about technical innovation, workforce development, and job creation. Let's talk about the other 2 buckets, and let's talk about collaborations. So Margaret, Mark, and I conducted more than 25 interviews, and it struck us how we kept hearing the same words over and over again. And I've tried to capture that here with this word cloud, which was created from the notes from the interviews. Just want you to notice the four biggest terms: relationships, collaboration, networking, and partnerships. And here are some quotes, the voice of the customer, about collaboration. I'm going to give you about 20 seconds to read these because there's some really good ones here. All right, so how has IACMI catalyzed this collaboration? Well, not too surprisingly, by convening and connected. They have convened annual members meetings, which feature technology updates, market updates, and snapshots of innovative SMEs. Since 2015, these meetings have attracted more than 4,500 people, and they represent excellent networking opportunities. IACMI has also convened working group meetings of their 5 working groups. These are more frequent, and they have been virtual, especially during the pandemic, and in person. They identify key issues and challenges, and they create ideas for new projects. And I have been fortunate to be the co-facilitator of the Infrastructure and Construction Working Group. I want to finish up this section by talking about IACMI's impact on SMEs, small to medium enterprises. And it's important to note that more than 70% of IACMI's industrial members are SMEs. And this is an area, a group where IACMI has definitely had an impact. And it's fair to say that IACMI has created an ecosystem of collaboration where SMEs can thrive. And here is the voice of the SME. I'll give you about 15 seconds to read these. And as you do, I want you to note the number of different benefits that are mentioned. So this slide summarizes IACMI's impact on SME. I've already talked about a lot of these bullets. I'll just focus on these 3 because I haven't talked about them: de-risking of new technology, validation of business models, and recognition as awards. And as evidence of the last bullet, here's a picture of the Vartega and Mito Materials winning the ACE Award for Infinite Possibilities at ACMA's Big CAMEX trade show in 2023. They created a product together called Phoenix Fiber Plus, which combines Vartega's recycled carbon fibers with Mito Materials graphene coatings to enable the production of thermoplastic parts with greater strength. So their products were stronger together, but they were stronger together. Vartega and Mito Materials were stronger because of this collaboration, and it was actually Dale that catalyzed this collaboration. I want to talk a little bit about leveraging IACMI's resources and reputation. And the first thing I need to do is define leveraging. The best way to describe leveraging here is I want you to think of George Bailey, Jimmy Stewart, in the classic Christmas movie, It's a Wonderful Life. Because of George Bailey, a lot of good things happened to other people. That's what I mean by leveraging IACMI's resources and reputation. Because of IACMI, other good things have happened. It could be additional funding for a university. It could be an additional investment in or by a company. And this table gives you some leverage dollar stats. The first line item has to do with workforce development. I mentioned the success of the intern program. That motivated the Department of Defense to invest more than almost $70 million in those workforce development programs that I've talked about. The DoD views workforce development as a core competency of IACMI. Let's move down the table. Because of IACMI's reputation and resources, its university members have received more than $53 million in additional funding from a variety of agencies, and Oak Ridge and NREL have received more than $36 million in funding. There has been investment in new facilities and investment in startups. TPI invested more than $25 million to grow its automotive business. And just this past year, the EPA gave a $6 million grant to IACMI and ACMA for a program called Circle, which is intended to show that composite construction products can be used to lower greenhouse gas emissions. That's the third federal agency now providing support to IACMI, the DOE, the DOD, and the EPA. So leverage. I want you to think about George Bailey. Because of George Bailey, a lot of good things happened. Because of IACMI, there's $220 million of good things. So to summarize, I'll come back to this slide and use Chad's description that IACMI's impact was better products, better processes, and better people. I hope in the past 25 minutes or so that I've helped show how Margaret, Mark, and I used our stories and stats to quantify that impact. If you add up the 4 buckets and add in convene, connect, and catalyze, that all equates to economic growth, capital investment in new facilities, job creation, sales of new products, and in additional investments. And here are the final stats quantifying IACMI's impact. I've told you about more than $400 million for the infrastructure of innovation. I've told you how IACMI has catalyzed hundreds of new design and engineering and manufacturing jobs with the potential for thousands or tens of thousands more because of those workforce development initiatives. I've told you about the sales of new products, dozens of new innovative products in different industries and throughout the value chain. And I've told you about more than $220 million in additional funding and investment. I'll come back to this one last time. I've shown you the ecosystem, and I've actually added a few logos for the funding agencies and for those workforce development programs that I told you about. IACMI has created an ecosystem of innovation that continues to expand and evolve. And the economic growth that has been catalyzed by IACMI will continue for decades. Just want to finish up with some acknowledgments. First of all, Margaret, Mark, and I would like to thank all the people that we interviewed, all the people who filled out our questionnaires, who answered our follow-up questions. Thank you for providing the stories and stats that I've talked about today. I also want to thank all the people who have been involved in IACMI, both past and present. It's really your story that I've been telling today. And I want to finish with one special acknowledgement, and that goes to Dale. And because Dale has really been involved in IACMI from the very beginning, and there has been a lot of change during those times. A lot has changed, but Dale, you have been a constant, a very important constant. You were the chief commercialization officer. You were the interim CEO for a while. You've written project proposals. You've negotiated contracts. You've organized things like innovation insights, and the list goes on and on. Your fingerprints are on everything that I've talked about today. And thank you very much for everything that you have done. That concludes my presentation. I want to thank you for your attention, and I think we have just a few minutes for questions.
I appreciate those kind words, Joe. Not sure they're fully deserved. It's taken a lot of people to do what's been done here. So,
Well, your fingerprints are on everything, and you deserve a very well-deserved pat on the back.
I appreciate that. So, yeah, we do have a minute or so if there are questions. I just see lots of comments. Mostly just congratulations and good job, Joe. Appreciate that. Also great job to Maha and Paramita. Thank you for your presentation as well. And I'll remind everybody that this will be recorded or has been recorded and will be on our website here in a few days. And so everybody who signed up for this webinar, whether they're able to make it or not, will get a reminder of that and a chance to go back and see it again. So appreciate that. And I wish all of you a great rest of the month of January and a great 2025.
Thanks, Dale.
And we'll see you next month.
Bye.
Bye. Thank you.